So now we come to the last problem of Unit 6, and actually the last problem for our entire course, aside from the final exam at least. Now you have a chance to put together all of the information that we gave you in Unit 6 to create a 2D wildfire. We're going to be looking at a big grid of forest and seeing how diffusion, heat loss, wind, and combustion come together to affect the time derivative of the temperature. As we've talked about before, these four factors can simply be added together to show how T changes with time. Let's look at the code for a second to figure out what all we're going to ask you to do. Here you can see we've given you a number of different constants that are going to help you out a lot. One thing that's kind of a small detail, but that might be interesting to note, is that the velocity due to the wind, which we can see right here, is actually very low. It's much lower than the velocity of the wind itself, since the fire is only going to follow the wind at a fraction of the wind's real speed. So as I said earlier, your first task is going to be to take into account heat diffusion, heat loss, wind, and combustion in the 2D heat equation right here. Fortunately, we're not going to ask you to use the implicit method that you used in Homework 1. You can just use the explicit method we used before, so basically the Forward-Euler method. An important thing that we need to deal with in this problem is spatially varying conditions. We must be careful to not introduce any hard edges anywhere, or they'll probably lead to artifacts. First from the solver, due to huge values in the derivatives, and second in terms of the model itself. We want to make sure that we don't see any staircases or pixelated contours, or really anything that doesn't look like reality. To help deal with this, we've already included a smooth Gaussian bell shape for the initial distribution of the temperature. The second thing that you need to do, however, is to create an initial distribution for the wood density. Now, I'll give you a little bit more information about that right now. Remember, the grid that we're creating using the code is basically making a map of the terrain that we're looking at. This graph right here is going to give you an idea of what we're looking for in terms of wood density distribution. Now here we have a bunch of lines that are parallel to one another, but slightly displaced. X and Y are actually just the physical coordinates that we're looking at, but the different colors of the different lines correspond to changes in the wood density at each location. So every point along the blue line is going to have the same density of every other point on that line. Every value on this purple line has the same density, and so on and so forth. In the code, we created two constants for you, wood 1 and wood 2, which have underscores in the code. It will be very clear what they are referring to. And these mark out the highest and lowest possible values of wood density that we have in our forest. Now, all of these lines are parallel to one another, and we've given you the slope in the code. So that means that the only factor differentiating them from one another is their y-intercepts. If we make a graph of wood density versus y-intercept, then we get something that looks like this. You can see that we're only letting wood density vary between wood 1 and wood 2 right here. Another hint that might be helpful when you're doing this problem is that you can solve for the y-intercept of a given line by saying that the y-intercept equals some y value minus the slope times the x value at that point. This is kind of a tricky problem, but remember, it's your very last one before the final. If you have any trouble, come to the forums. Good luck!